In today's lecture, we are going to learn algebra of real functions. So we are assuming two functions. Let f be a function from x to r and g be a function from x to r. B2 real functions then for all x belonging to x, number 1, f plus or minus g of x will be equals to f of x plus minus g of x. That is, if we have f plus g of x, it becomes f of x plus g of x. Or if we have f minus g of x, then it becomes f of x minus g of x. Second point, for any, say, alpha belonging to a real number, alpha into f of x will be equals to alpha into f of x. The third one, f into g of x will be equals to f of x into g of x. And number 4th, f by g of x is equals to f of x by g of x. Now if the denominator is 0, what happens is the value becomes undefined. So the denominator should not be 0, so provided g of x should not be equals to 0. Okay, let's deal with an example relating this. Let f of x equals to root x and g of x equals to x be two functions defined over the set of non-negative real numbers. Find f plus g of x, f minus g of x, f into g of x and f by g of x. So solution. Okay, first of all, one very important thing to note over here is that this B2 functions defined over the set of non-negative real numbers. This has its own relevance. In junior classes, something written like this we might have ignored when we were small, but now it's no more ignorable. We need to be very careful what we are writing. Here they have written non-negative real numbers is because we have root under x. Now if root under we take a negative number, it becomes imaginary, it's not a real number. That is why they have defined as non-negative real numbers. Now f plus g of x equals to f of x plus g of x. That will be equals to root x plus x. F minus g of x equals to f of x minus g of x, which is equals to root x minus x. F into g of x equals to f of x into g of x, which is equals to f of x is root x into x. So this becomes equals to x to the power half into x, that is x to the power 3 by 2. Powers gets added on multiplication, and the last part f by g of x will be equals to f of x by g of x, where g of x should not be equals to 0. So this is equals to f of x is root x by g of x is x, and denominator should not be 0. So x not equals to 0. So this is equals to x to the power half by x not equals to 0, which is equals to x to the power minus half. On division, powers get subtracted. Half minus 1 will be equals to minus half. That is why we have x to the power minus half, where x is not equals to 0. So this is a very simple way in which we solve this type of problem. Okay, so with this you are now capable of solving the second exercise of the third exercise of the chapter. Now we'll begin with some miscellaneous questions from inside the chapter. So first example. Let R be a relation from the set of rational numbers to the set of rational numbers defined by relation R equals to a comma b, such that a comma b belongs to the set of rational numbers, and when we subtract a minus b, this should belong to the set of integers. So this is our relation. We need to show that number 1, a comma a belongs to the relation for all a in Q. Number 2, a comma b belongs to relation should imply that b comma a belongs to the relation. And number 3, a comma b belongs to relation and b comma c belongs to relation should imply that a comma c belongs to the relation. Now how are we going to prove is that, let's take the first part. So we need to show that a comma a belongs to relation for all a belongs to the set of integers. So for any a belonging to the set of rational numbers, a minus a is equals to 0. So we needed to show that a minus b, when it was a comma b, a minus b should be integer. So a minus a is 0 and 0 is an integer. So therefore a comma a belongs to the relation because a minus a is 0, which is an integer. So any rational number a we take, the subtraction of a minus a, we get 0, that is an integer. So a comma a belongs to the relation R. Second part, it is given to us that a comma b belongs to relation. From here we need to prove that b comma a belongs to relation. So a comma b belongs to relation implies that a minus b, the subtraction of this integers, will be an integer. So this implies minus of a minus b is an integer, because if 5 is an integer, then minus 5 is an integer. If minus 28.28 is integer, then minus of minus 28, that is 28, will also be an integer. So if we take a negative of an integer, that is again an integer itself. So this implies minus a minus minus plus b belongs to integer. Now b minus a belongs to integer implies b comma a belongs to the relation R. So therefore a comma b belongs to relation implies that b comma a will belong to the relation. Now the third part, a comma b belongs to relation implies and b comma c belongs to relation implies that a minus b belongs to integer and b minus c belongs to integer. So now addition of two integers is an integer. So this implies a minus b plus b minus c is also an integer. When we add two integers, then the result is an integer. So minus b plus b cancels off. This implies a minus c is an integer, which implies a comma c belongs to the relation R. So hence proved. So this is how we solve this type of question. the next one, example 2. Let f equals to 1, 1, 2, 3, 0, -1, -1, -3 be a linear function from z into z, find f of x. Okay, so linear function basically means that the function f of x will be in the format of mx plus c. Why mx plus c? Because this is a linear graph. That is why we take mx plus c. So this implies f of 1 is equals to m into 1 plus c, and f of 1 is basically 1 equals to m plus c. Now putting x equals to 1, putting x equals to 2, f of 2 will be equals to m into 2 plus c, and f of 2 is basically 3 equals to 2m plus c. Now we take this as equation 1, this is equation 2, equation 2 minus equation 1. So c minus c cancel out, 2f minus m is n, 3 minus 1 is 2. So m is equals to 2. Replacing m equals to 2 in equation 1, we get 1 equals to 2 plus c, which implies c equals to -1. Therefore, f of x equals to mx plus c is -1, which implies f of x equals to 2x minus 1. So this is our linear function. Okay, next question. Number 3. Find the domain of the function f of x equals to x square plus 3x plus 5 by x square minus 5x plus 4. So whenever we need to find a domain, simple tricks that we need to remember. If there is a root, the value inside the root should be non-negative. Now whenever there is a division, the denominator should not be equals to 0. That's the simple trick when we use to find domain. So here x square minus 5x plus 4 should not be equals to 0, which implies x square minus 4 plus 1, Milton breaking, we get 4 plus 1, 4 into 1 is 4, x plus 4 should not be equals to 0, which implies x square minus 4x minus x plus 4 should not be equals to 0. So x minus 4 minus 1, x minus 4 not equals to 0, which implies x minus 4, x minus 1 not equals to 0. So this implies, so this is not equals to 0. This implies neither x minus 4 should be equals to 0 nor x minus 1 equals to 0. See, we can either write, we can write either x minus 4 not equals to 0 or x minus 1 not equals to 0, or we can also write in this way that neither x minus 4 equals to 0 nor x minus 1 equals to 0. Let's write either x minus 1 minus 4 not equals to 0 or x minus 1 not equals to 0. So this implies either x not equals to 4 or x should not be equals to 1. So from here we conclude that therefore the domain of f is the set of real numbers minus what all can't we put in this, that is 1 and 4. So this is our solution. Example 4. And with this example we'll conclude the chapter. The function f is defined by f of x equals to 1 minus x when x is less than 0, 1 when x is equals to 0, and x plus 1 when x is greater than 0. So draw the graph of f of x. So what happens over here is, for the negative terms we use this one, for 0 our value is 1, and for the positive terms we have the equation x plus 1. So therefore for x less than 0, say we put x as minus 1, then we get f of minus 1 equals to 1 minus x, that is 1 minus x is minus 1, we get 1 plus 1, that is 2. F of minus 2, any 2 points, finding any 2 points is good enough because this is a linear equation. So for a linear graph, what happens is, if you have 2 points, you just need to make a straight line through the 2 points. So f of minus 2 over here is 1 minus minus 2, which is equals to 3. Say for security we find the third point as well. So 1 minus minus 3, which is equals to 4. For x greater than 0, f of 1 will be equals to x plus 1, that is 1 plus 1, 2. F of 2 equals to 2 plus 1, 3. F of 3 say will be equals to 3 plus 1, that is 4. So how will this graph look like? So first of all, as you must have already noticed, either we are taking negative or positive, we are getting only positive values. X, x prime, y, y prime, origin, minus 1, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, 1, 2, 3, 4, 5, 6. So f of minus 1 is 2, minus 1 is 2, f of minus 2 is 3, and f of minus 3 is 4. F of 0, this was given in this itself, was 1. F of 1 is 2. F of 2 is 3. And f of 3 is 4. So we get a straight line here in this way. We get a straight line here and this way. So this is basically our graph of function f of x. So with this we conclude today's lecture, and with this our chapter is completed. Thank you.